Good day everyone, and welcome to the second video in a series investigating the relationship between continuity and differentiability of various types of functions. In the first video, we had the algebra fun of finding the right-hand derivative and left-hand derivative of a given polynomial to show that aside from its continuity, it is also differentiable, because the right-hand derivative and the left-hand derivative are equal. Now let's enjoy the celestial symphony by visualizing the differentiability of the said polynomial through a GeoGebra construction. Let's execute these construction steps, so please observe and feel free to recreate this GeoGebra construction. So step 1, type the function f of x is equal to x squared plus 3x plus 2 in GeoGebra to plot the polynomial. So we type x squared plus 3x plus 2. Here is now the graph for the polynomial x squared plus 3x plus 2. Then step number 2, create the point at x equal to 1 by typing 1, f of 1 in GeoGebra. This will place a point on the graph of the polynomial at 1, 6, denoted as point A at 1, 6. We type 1, f of 1, and we are getting point A at 1, 6. Step number 3, by inspection, observe the graph of the polynomial. Since the polynomial is continuous and smooth, it does not have any breaks or discontinuities, confirming that it is continuous at any point of the number line, including point A. So we don't have any breaks here or discontinuities, right? Step number 4, draw a line tangent to the curve at A16. Use the tangent functionality in GeoGebra to draw this tangent line. Let's click here, and then tangent, then click point A, and then the curve. Step number 5, determine the slope of the tangent line. This slope represents the derivative of the function at x is equal to 1. Click here, and then slope, and then click on the tangent line. So the slope is 5. M is equal to 5. The output after executing the slope functionality is M is equal to 5. This can also be found in the output after executing the tangent functionality. We have the point slope form y equals to mx plus b, where M is the slope. Hence, the slope of the line tangent to the curve at A16 is 5. Step number 6, find the derivative function by typing derivative of f of x in GeoGebra. This would generate the derivative function f prime of x, which is a linear function in this case. So let's type derivative of f of x. Now let's investigate the output of the derivative command in GeoGebra. So after typing derivative of f of x, we got the linear function 2x plus 3, which represents the slope of the tangent line at any point x on the given polynomial. The x coordinate in this derivative function corresponds to the x value in the original polynomial, right? And the y-coordinate of the derivative function gives the slope of the tangent line at that x value. Step number 7, find the derivative at x equal to 1 by typing f prime of 1 in GeoGebra. This value represents the slope of the tangent line at x equal to 1 or at point A16. So we type f prime of 1. So please observe, so after typing f prime 1 in GeoGebra, we got f prime 1 equals to 5, meaning the slope of the line tangent to the curve at A16 is 5. Now let's type the ordered pair 1, comma f prime of 1. We now have point B along the derivative function, right? And our point B is at 1, 5. And after typing the ordered pair 1, comma f prime 1 in GeoGebra, we got f prime of 1 equals to 5, meaning that the slope of the line tangent to the curve at A16 is 5. After typing the ordered pair 1, comma f prime of 1, we got the point B, 1, 5, which lies on the derivative function in blue. Here, 1 is an x value from the original polynomial, and 5 is the slope of the tangent line to the polynomial at that point A16. Thus, we can say that the points on the derivative function are ordered pairs where x represents any x value from the polynomial and y is equal to f prime of x represents the slope of the tangent line to the curve at the corresponding x value. Thus, we have a set of x values from the polynomial for the derivative function with the corresponding set of y values which represent the slopes of the tangent lines at those points. Let's have another x value. Let's have x equal to 2. So we type 2 f of 2. And then we also type the ordered pair 2, comma f prime of 2. So we have 2, 7. And 2, 7 is indeed along the derivative function that is in blue here. Here are our observations. So the graph of the derivative function f prime of x shows a linear relationship with x. The derivative function has a set of points x, f prime x that provide the slope of the tangent line to the curve at any point x. At x equal to 1, the slope of the tangent line is equal to the value of f prime of 1, demonstrating the relationship between the function and its derivative. Let's further enrich our GeoGebra experience by exploring the relationship between continuity and differentiability in the next video, where we will construct a GeoGebra applet that illustrates the limit definition of the right-hand derivative and the left-hand derivative. We will have a GeoGebra applet to create and explore. So thank you so much for joining me today, and I hope that you have learned something.